Good morning, good afternoon, or good evening. No matter where you are located in this world, the future of air travel is incoming, and our product engineering team is at the forefront of innovation. They have designed an eVTOL vehicle that addresses reduced mobility passengers. Tiffany, tell us more.
First off, what is an eVTOL? It's an electric vertical takeoff and landing vehicle that's completely powered by renewable energy. The development in eVTOL aircraft can have a significant impact on our infrastructure, technological development, environment, as well as ergonomics. Since the number of passengers that are utilizing public transport are increasing every year, having another mode of transportation, namely urban air mobility, can help to alleviate that yearly increase. The development of more efficient renewable energy is an important technological impact, and this technology can help to reduce the CO2 emissions from commuter traffic. Something that our team is focusing on is also the ergonomic impact. This eVTOL design is going to be a fresh opportunity to incorporate accessibility for disabled passengers. Now, we realize that we're not the only startup trying to enter this space and industry. There are other groups such as Joby Aviation and Kitty Hawk, which have some level of certification, some level of prototyping and testing either complete or underway, but neither of these companies have managed to enter the urban deployment phase. Because of that, our company has an opportunity to catch up. And the same goes for Velocity and Archer. The information that we found on these startups is that they're able to accommodate passengers and pilots, but nowhere do they really mention the focus on disabled passengers. There are many different stakeholders in our project. Passengers with reduced mobility are the first and foremost priority. They would like for this aircraft to be safe, comfortable, as well as affordable. Some other groups which would have a stake in our eVTOL aircraft would be the local community, since these would be deployed in residential areas, air traffic control, as well as electric propulsion engine suppliers. From these stakeholders, we were able to derive a list of their implicit and explicit needs. This includes configurable cabin seating for those with disabilities, cabin navigation for people who are having difficulty navigating physical space, ingress and egress support equipment, completely battery powered, ability to travel a certain distance, etc. Now, our team has mentioned a couple times that we want to design our eVTOL with the disabled passenger in mind. And why is that? Disabled people struggle every day navigating these traffic dense areas, um, and some of their disabilities are impacting the way that they navigate physical areas, such as the ability to climb stairs, navigate uphill terrain, navigate curbs and sidewalks, etc. And then there are some disabilities that are not too obvious to the eye and impacts their ability to operate vehicles like cars, such as people with limited eyesight and hearing. All in all, navigating the world is just highly stressful and uncomfortable for some of these individuals, especially in an area where the disabled person is not the primary user. And thus, we want to make them the primary user that we're designing for. And so our main mission is to design an eVTOL vehicle that offers accessibility and comfort to travelers with and without a wide range of disabilities. We have identified several constraints, and we'll be addressing some of those later on in our risk management. Our concept of operation starts at the takeoff site. After taking off, whether it be from an urban, suburban, or rural area, the vehicle will be communicating with other aircraft, air traffic control, and other information sources during the flight. Uh, it will, of course, navigate the urban areas safely, which have a lot of tall buildings. And after landing at point B, the cycle starts all over again. And now I'll hand it off to Robert.
Thank you, Tiffany. I am Robert. I will first go over the functional architecture of our project. The diagram was built using a powerful tool, SysMML. At the top of the architecture is the system of this mission, eVTOL's air taxi for passengers with reduced mobility. The design team derived from this system 7 subsystems. While deriving this, the focus was put on what the system is going to be able to do. Here are those 7 subsystems. Control and maintain flight path, operational safety, allow simple ingress and egress, meet standards and regulation, performance, environmental comfort, and carry load. From each of those systems, we came up with the requirement. For instance, looking at the second functional requirement here, carry load, we have 3 subsystem requirements: passengers, battery, and baggage. Each and every one of these subsystems have to relate to the main system by either satisfying it or verifying the requirement. As shown here in the environmental comfort subsystem, there are a few different requirements. If we pick maintain temperature, the vehicle must stay between 50 and 80 degrees, which require AC unit, which in this case the AC unit will satisfy this requirement. Moving on from the functional architecture into the high-level functional flow block diagram. Here, the design team focuses on logical sequence of what must happen for each trip. First, there are input functions stated here. The next part is at the top of the diagram with the 7 functional requirements previously discussed. The eVTOL must take those functions and operate with its exclusive accessibility diagram, which will result in a safe and comfortable delivery of passengers to their destination. This will apply to every trip of our vehicle design. Earlier, Tiffany did a great job of explaining the stakeholders' need. We used those to obtain these engineering characteristics. This process took a few attempts to make sure every single part of the vehicle design was taken into account, from control path, environmental comfort to standards and regulation. With this characteristic, the design team used the QFD to show the correlation between stakeholders' needs and their engineering characteristics. For instance, one of the stakeholder needs is having tactile surfaces, and we find it as our engineering characteristic as well. You can imagine that the relationship is positive for this customer need and its respective engineering characteristic. Yet, looking at the correlation between tactile surfaces and flying at a set altitude of 2,000 feet, you can imagine that there is no relationship whatsoever between those two. Here is the QFD in question. It was used to ensure that the stakeholders' needs are well represented in the engineering requirement. As shown here, there are different parts of the QFD. All 11 house of qualities or rooms serve a specific purpose to make sure we gain the greatest value for the customer. Every room will not be talked about, though every room was meticulously worked on by the design team to ensure the quality of the design so that the stakeholders are in fact satisfied. Tiffany earlier highlighted the pros and cons of our competition: Joby Aviation, Velocity, Archer, and Kitty Hawk. By looking at this comparative assessment, it is visible how the other 4 different competitor ranks with respect to the customer requirement and support what Tiffany mentioned. Similarly to the previous room, here it compares the competition to each engineering characteristic. The competition designs failed to be equipped for passengers with reduced mobility, as shown here and supported in Room A. Another reminder of why our design is better for passengers with reduced mobility and is evident after looking at how companies fail to accommodate for all passengers. The last 2 rooms of the QFD are technical difficulties, which simply ranks the ease at which the engineering characteristics can be achieved, and the other room contains target values of those engineering characteristics. From the QFD, the design team was able to come up with specific, measurable, achievable, relevant, and traceable high-level requirements. To illustrate this, here is an example. To sum it up, the design team used a QFD which in itself has parts that work together by analyzing them and interpreting the result. Small requirements were obtained to satisfy and generate great value for the stakeholders. Now, up next, William will be discussing system decomposition.
Thank you, Robert. Now, to better study our aircraft, the design team broke it down into 6 separate subsystems. For the sake of time, we have decided to choose what we believe is the most important subsystem to further decompose: the payload, as achieving both the power and energy requirements at a low battery weight is essential for the aircraft to even take off and land safely. We have then listed some requirements derived from the RFP alongside some different values that were used in creating our parametric diagram. A simple parametric diagram is built for the payload systems. Formulas were developed to first account for all types of luggage, carry-on, checked, and medical equipment, so that was added the weight of a passenger to finally get the weight of a single passenger with their luggage. We then added up that number for all the passengers to get the total load, to which we added the empty weight of the aircraft to get the overall takeoff weight of the eVTOL. Now, as you may have seen, there are multiple requirements. The top-level customer requirements were weighted against each other. These requirements were prioritized in the final design of the vehicle. We down-selected safety, green energy, transportation of disabled passenger, VTOL capability, and a reconfigurable cabin that can transport 2 passengers with reduced mobility and hidden disabilities, or 4 passengers. While having the top-level system requirements in mind, the most critical parameters were defined by the product design team. The next step was to define a metric to evaluate each parameter and to define success criteria to gain customer acceptance. For example, to ensure safety, we want to be able to evacuate passengers in less than 2 minutes. After wrapping up the technical aspects of the project, we are now moving to the fun part, the design of our aircraft. We have reviewed multiple designs out there, but unfortunately, none of them are really inclusive. So, what we did is that we have come up with multiple alternatives with different options. And for the sake of time, we have shortlisted the 8 most important ones, from the cabin arrangement to the number of engines and the energy source. We have used the different alternatives and options to put together 3 different designs using the morphological matrix. We have then evaluated them with a simple weighted coefficient method. The 8 initial alternatives were split into 2 categories. On one side, the aircraft design, with the cabin arrangement being the most important alternative. Design 1, as you can see, is better by a large margin. On the other side, we have power generation. The number of engines is the top alternative here. Again, design 1 is the favorite in the game. Both sections are then combined here to have the overall weighted total. Both portions have equal importance. The first design is clearly our winning design by far. The design has a configurable cabin as per the instructions, and because it is the most efficient option to carry a maximum number of passengers on one trajectory. To allow simple ingress to the aircraft, a ramp was designed. The fixed landing gears can absorb the shock in case of a crash, and having an aerodynamically shaped aircraft means tailless fare is chosen. Our aircraft will have 6 engines, and like many of the currently tested eVTOLs, a Li-ion battery is used with tilt rotors to increase the lift and hovering capabilities. Now we will be unveiling our design. Drum rolls, please. Take it away, Saqib.
Thank you, Liam. My name is Saqib Ahmed, and I'll be starting off with the concept of our design. Now, lo and behold, the conceptual design of countless of hours of synthesizing customer requirements against design limitations. Some of the key parameters of our eVTOL aircraft include 6 engines with 6 tilt rotors that allow our aircraft to operate with one engine inoperable and allows for optimized handling characteristics, which all increase the safety of our passengers. A full, spacious, configurable cabin with the option of up to 4 seats that allow for comfortable transport, all within the proximity of one's medical equipment. A tailless design was selected to fully optimize egress and ingress in case of emergency situations. And finally, a fixed landing gear with shock-absorbing properties was selected for simplicity to reduce overall maintainability costs and increase overall safety. I know. It all seems too good to be true. So the product engineering team has put it upon themselves to put together a verification matrix to fully verify and validate each requirement against its target values. We have a wide range of tests stemming from flight tests to inspections and plain old measurement tests. The next few slides will cover our verification matrix. Other than the traditional flight tests and ground tests, our team wants to deploy a full-scale cabin mock-up to fully verify and validate spacing constraints for our passengers. Like most electric vehicles, it is important to quantify energy usage per mile and passenger. Like all great marvels of engineering, with great innovation comes great risks. So our product team has formulated a risk register to proactively find ways to mitigate risks before coming into fruition. 2 of our most concerning risks are related to bird strike and battery fires. In this chart, you'll see a sample of the necessary steps the team has taken action in in order to mitigate these risks. In conclusion, our design of an electric VTOL vehicle encompasses what the product design team believes to be the most critical aspects for our stakeholders: to promote a safe and carbon neutral flight for disabled passengers that don't have the luxury of air travel at their own convenience. This vehicle will be able to take off and land within a minimal footprint to allow for quick turnarounds, which lowers personnel required for flight, ultimately lowering the operation cost. The simplistic yet configurable design of the aircraft allows this aircraft to be fully customizable, such as for emergency response or disaster recovery, where all the amenities are already on board the aircraft to promote a safe and effective environment for reduced mobility passengers. The design team has already started planning for the future of this aircraft, where innovative power generation techniques can be applied to sustain longer flight. Skydweller Aero, for example, has been testing an aircraft with solar panels spanning their wingspan to generate power for sustained flight. We are also keen into looking into advancement in battery technology. Like Tesla, who manufactures their own batteries, they have been able to increase their range and power from their preliminary designs. 70 to 80% of all aircraft incidents are attributed to pilot error. To promote a safer flight for our passengers, the engineering team is looking into autonomy, which would not only increase the safety of the aircraft, it would allow for more passengers or equipment on board, ultimately increasing value for our stakeholders. This concludes our presentation. I want to thank Dr. Garcia and our engineering team. Thank you.